the topic for today is elimination theory, and I've decided to take a fairly historical point of view, partly because it's a very classic subject in algebraic geometry, and also the way that the relation between algebraic geometry and elimination theory is sort of fluctuated over the years, and it sort of explains where things are now if we understand sort of how we got to them. And so the topics that I'm going to discuss is, the title of the talk is elimination theory in the 18th and 19th century, and that's why I'm going to start in the 17th century, and just tell you a little bit about Newton and Tschirnhaus, and then we're going to go to the 18th century and talk about Kramer and Bezout. And so that's a paper of Bezout, his first paper on elimination theory. Then that's his 500-page book on Bezout's theorem. And so how do you spend 500 pages on Bezout's theorem? Well, we'll see why. And Waring's algebraic meditations. Then we'll actually go more deeply, because of course Bezout had lots of theorems, not just the one that has his name attached to it. And that's sort of be the 18th century. Then sort of a transitional figure is Poisson, right at the beginning of the 19th century. And that's the famous Poisson formula comes from for resultance. And then we'll talk a little bit about resultance in the 19th century. I'm not actually going to say a huge amount, just because it's a gigantic subject, as we'll see. And then I want to give 3 examples of sort of how people worked with resultance in the 19th century. So we'll see a paper of Minding, where he actually did what we now think of as a mixed volume computation. We see Bonnet sort of trying to think about sort of multiplicities and how they relate to resultance. And we should just see Riemann, who was just a user of elimination theory, and sort of how did Riemann think about some of this stuff. So that's sort of the outline for the talk. So to get started, here's a manuscript that Newton wrote somewhere in this 5-year period in the 1660s, and it was a mixture of Latin and 17th century English. And so to read his quote, so the Y is a TH, so that's the, and here's the word that. And so once you translate those, it makes pretty good sense. And of course, this is Latin. And so basically, given 2 curves, invent or find their points of intersection. And he says this is a principle rather than a problem. But notice it's a geometric problem, because you have the curves, you want their points of intersection, but rather propounded of the algebraical, then geometrical. So the idea is to get the geometry, you have to do the algebra first. So he's actually saying that already. And this is done by eliminating one of the 2 unknown quantities out of the equation. So already there's elimination occurring in the 17th century.
Actually, David, elimination occurred, I think, in the first millennium. Chinese mathematicians could do equations.
Oh yeah, so here, yeah, certainly for linear equations.
No, polynomial equations.
Oh, even probably, yeah, oh yeah. So here, of course, I'm talking about sort of in Western Europe, but you're right that other parts of the world had done elimination well before this. In fact, for example, there's some interesting Japanese work on elimination theory that I'm also not going to mention. And but it turns out that, so he says that it appears there are so many cut points as the rectangle of the curve's dimensions. And basically that's Bezout's theorem, because you just take the product of the degrees. And so here's Bezout's theorem roughly 100 years before Bezout wrote his first paper. And so it was just sort of well known. And then but here we're thinking about things geometrically, but then we can also think algebraically. So this is a Tschirnhaus writing in 1683, and this is the so-called Tschirnhaus transformation, because they were trying to solve algebraic equations. And Tschirnhaus came up with a pretty cool way to try to solve this cubic equation. So the idea is you think of Q and R are known. Those are your coefficients. And so you want to figure out what the roots are. Of course, they knew the formulas going back to Cardan, but they wanted sort of efficient ways to find those, because those ways might generalize to higher degrees. And so that was really their goal, was to find something that worked for not just cubics, but quartics and so on. And so what he does is he does this substitution. So z is a new variable, and it's related to the previous variable y by a quadratic transformation, and where a and b at this point are unknown coefficients. So the idea is we're going to make clever choices of a and b to do things. Then, and of course he's writing in Latin, so this is an English translation. Following from this, let there be a third equation by proceeding according to the recognized rules of analysis. So notice he's already saying we know how to do this in the 17th century, and which the quantity y is absent, and we shall obtain, and this is the cubic polynomial, and I left off the constant term, which is pretty complicated. And Chernow's idea is I want to choose a and b to make these coefficients vanish. Because once I make those guys vanish, then I just get z cubed plus a constant equals 0, that's just a cube root. And so, and of course right here, remember that Q and R are the known guys. So of course this one tells me exactly how to pick A. And then once I've picked A, and I know Q and R, here's a quadratic in B. So of course I have to take a square root to get B. And then once I do that, those go away. Then I take the cube root, and so we get the solution to the cubic equation. So here's elimination used in a purely algebraic context. So already, even in the 17th century, we have elimination used for geometric methods and also in algebraic methods. So it was clearly pretty well established early on. Now, let's go to the 18th century. And so Kramer, so this is how Kramer stated things in a paper he wrote in 1750. And I have to warn you that this is my bad translation from the French. And so you'll see that there's places where it's not quite elegant. So if one has two variables and two indeterminate equations, one of which has order m and the other order n, then by means of these equations, one of these variables is chased out. So like I say, that's a bad translation, but I couldn't figure out a more graceful way to say it. So you get rid of one of the variables. The one that remains has a final equation of at most mn dimensions. So there's again, Kramer's rule stated pretty clearly, and this is again 14 years before Kramer's first paper, or before Bezout's first paper. So this is a statement of Bezout's theorem. Now Bezout did have a theorem in his first paper, but he did more than just sort of the classical version of Bezout's theorem. And in fact, he actually also, there's a lot of other work going on, like Euler had some work on stuff like this. But here, let's take our two polynomials. But the idea is that instead of just, talking about the degrees, so in this case, m plus p is the degree of this one, m prime plus p prime is the degree of that one. So those are the degrees, but let's further restriction that I'm going to put a bound on x. So here it's bounded by m, here it's bounded by m prime. And so these are the Newton polytopes of these two polynomials. And he wants to do elimination. And so he basically wants to basically get rid of x. And so what he does is he multiplies f and g by polynomials of the appropriate degrees. And then in this equation right here, you equate the powers of x, and of course there's no x's over here. You get a system of equations, and it turns out the coefficient matrix is exactly the Sylvester matrix on the nose, and this is 80 years before Sylvester.
So David, your polytopes, do you mean that m in the middle to be a p and the m prime in the middle to be an m prime? Like the m and above the m?
So that's the point. And so here I'm just giving the x coordinate. Yeah. So that's a, and of course.
So the y coordinate there.
So here the y coordinate is m plus p, and here the y coordinate is m prime plus p prime. Here the x coordinate is m prime, and again that m prime just means.
Okay. So the y coordinate p prime there.
Yeah. So the total. So this distance is m plus p. So this distance is m. That distance is p. Again, this distance is m plus p. That distance is m. And the point is, this has slope minus 1.
Okay. Gotcha.
Yeah. And so that's the crucial thing, is that so like I say, that has slope minus 1. And so again, he actually wrote down the Sylvester matrix, and when he eliminated x, he called this the resulting equation. And this is, I think, the first use of the word resultant in elimination theory. And so I think Bezout is the one that did reduce a resultant. And of course he got, he gave this formula for the degree, and it turns out, of course, that's an example of sparse elimination. And so when they talk about Bezout's theorem, well, Bezout actually did Bezout's theorem, but he did quite a bit more. And in fact, we'll see he did an astonishing amount more. Now, next I want to talk about two books. And so, in 1770, Waring published his Algebraic Meditations in Latin. And then in 1782, he brought out another edition. And then in 1779, sort of between these two, Bezout published his book, The General Theory of Algebraic Equations, which is it's a 500-page book on basically Bezout's theorem. And it turns out that Waring's book, this book actually was influenced by that one. So that part of the reason that Waring published his was to sort of say a few words about some of what Bezout had done. So what I want to do is I want to talk about Bezout's general approach, sort of what his philosophy was. And then I'm going to switch over to Waring, give a couple of extracts from him. So how did Waring describe Bezout's results? And then go back to Bezout. And Bezout had a classification of polynomials. And so we'll talk about that. I'll draw some modern pictures of his polynomials. I'll talk about one of his many Bezout theorems, and then I'll say a few words about his proofs. And so that's what we're going to do when we talk about Waring and Bezout. And so how does this work out? So here's, and so this is a quote from his book in 1779. So we conceive of each given equation as being multiplied by a special polynomial. Adding up all those products together, the result is what we call the sum equation. The sum equation will become the final equation through the vanishing of all terms affected by the unknowns to eliminate. So let's go through that a bit more slowly. And so the given equations, so here I'll call them f1 to fn in variables x1 to xn. So the idea is that we're in a situation where the number of equations matches the number of unknowns. So that's a pretty standard assumption they made when doing these kinds of problems. Then you multiply each by a special polynomial, and I'll give some examples of how, and special polynomial usually means you pick its Newton polytope pretty carefully, and typically by a degree bound, sometimes more sophisticated things. And then so you multiply each by that. And so then when then you take each special polynomial, multiply it by the given polynomial, add them up, and you get what's called the sum equation. And so, of course, that's something that should look pretty familiar that we've all seen. And then this becomes the final equation. And so that's what he says, the final equation, when all of the terms involving the unknowns to eliminate vanish. So let's suppose we're trying to eliminate x2 through xn. So I want basically what to be left is only stuff involving x1. And so that's what he's saying, is that he basically wants to, make things work. He wants to choose these special polynomials so that I end up in this polynomial ring just in one variable. And then notice, of course, we're really talking about an elimination ideal, because this is an element of this ideal, and of course to be in here means I'm in the intersection. So elimination ideals are definitely implicit in Bezout's approach. Now, one big difference is that Bezout, like most people in the 18th and 19th century, sort of worked with only finitely many polynomials at a time. And so they would sort of work with something like this. Here, you see, we're working with all of the polynomials and taking the intersection. And basically, part of the difference is that all of this is basically math before set theory. So they really didn't have a language for talking about all possible ones. They really just were interested in, the particular ones they were interested in. And we'll see that throughout their way of talking about this stuff. And so that's his general approach. Now let's talk about how did Waring talk about this in 1782. So here we had, he used h for the number of equations. and the various degrees. And they seem not to like indices back then, so they use things like this. And so in each of these H equations, you multiply H assumed equations. So the assumed equation, that's Bezout's special polynomials. And see, here you're making careful choices of the degree. And so it's the product of the degrees minus n, the product of the degrees minus m, and so on. And then it says, let the resulting equations be added together, equate to 0 the coefficients of each term of this degree, because the whole point is that if those are the degrees of the given equations and these are the degrees of the multipliers, then when you do the product, they have just the product of the degrees. And so basically you equate to 0. The point is here he's thinking about eliminating everybody except y. And so you set those equal to 0, and so you get a system of equations. And once the equation whose root is x or y or z cannot be of degree greater than this product of degrees. So this is sort of the general version of Bezout's theorem, now for n polynomials and n variables. And of course, this is the affine version of a Bezout's theorem, because of course they recognize that what they say here is cannot be of degree greater than this. So they're not asserting the number of solutions is exactly that, because some solutions might be an infinity and things like that. And so basically, again, just putting this in more modern language, you get a polynomial in one variable whose product is the product of degrees and the elimination ideal of the given polynomials. So this is how Bezout's theorem was really thought about, is that basically you're trying to find these nice, these ideals in the elimination ideal. And so that's one of his theorems. But again, Bezout had many theorems. So let me talk about another of Bezout's theorems. So again, we have our equations of those degrees, and they all involve the same unknowns. But now, instead of, see, this is of course a bound on the total degree. But now we're going to put some other bounds. We're going to put a bound on each individual degree as well. And so here the idea is that, so P, Q, R, S are the maximum degrees to which this appears in the first equation. Here's, the primes, that's the degrees to which they appear in the second equation. These are the degrees in which they appear in the third equation. And so here we're sort of, again, we're no longer sort of in the, what we call the dense case. We really got sort of a more sparse case because of these bounds on the individual degrees. And then again, when you try to come up with, you eliminate all variables but one, what you get is, and he actually gives the formula, that it's the product of degrees, but then there's a correction term dictated by sort of how these individual degree bounds interact with the total degree. And so that's sort of one of the Bezout theorems that was Bezout stated and Waring commented on. So that's pretty interesting. So we're talking about some fairly sophisticated things here.
So that doesn't reduce to the earlier. So if like PQRS are.
Well, see here I'm bounding every single one. In the previous one, I only bounded one of the variables.
I thought it was total degree in the previous bound.
And but remember in the previous, and so I think if you work it out, the notation's a little inconsistent, but I think if you work it out, it would work. And you'd have to pick one of the bounds. You'd have to pick the degree. You'd have to pick this to be the total degree to make it work out. But I think
That's bound of total degree, then all those, then P, Q, R, S are all N, P prime, Q prime, R prime, S prime are all N, and so on.
Yeah.
It looks a little different.
Yeah.
No, that's the same thing.
Yeah, that's the same thing. Yeah, so I think that works. Yeah. Yeah.
Okay.
And so let's go back to Bezout's book. And so what actually did Bezout do in 1779? So he had two bits of terminology. So the first was complete means you're using just all monomials of degree less than or equal to n. So that's sort of the dense case. And incomplete is where you put sort of restrictions. And these days we call that the sparse case. But he didn't talk about an arbitrary collection of monomials. He had very specific ideas about sort of the kinds of sparsity he wanted to do. And he organized incomplete polynomials into species. And the word species is actually pretty interesting because it's part of the intellectual framework of the time. The 18th century is when, like Linnaeus was doing his classification in biology, and where they organized things into species and genera and things like that. And so here, this is really borrowing from that sort of Enlightenment intellectual ferment about just trying to organize things. And here he's trying to organize mathematics and trying to organize these polynomials. So we actually had these various species, and so, for example, the second result of Bezout that I quoted in Waring, where you put the bounds on each individual degree, that's basically an incomplete polynomial of the first species. And so that's how he did it. But I want to talk about the third species, because that leads to some fun stuff. And so in this case, when n equals 3, so the third species, and this is the way Bezout wrote it, is that so K1, K2, K3, those are the exponents of the individual variables. So so T is basically a bound on the total degree. But then I bound each individual, X is bounded by A1, the degree in Y is bounded by A2, the degree in Z is bounded by A3. But then I also bound the pairs. And an example of that is this guy right here. So now, Bezout did not at all think geometrically about this stuff. So he would have never visualized something like this. But the idea is that, sort of here's the degree in X, here's the degree in Y, here's the degree in Z. And so that first bound, so this one right here, that's basically this face right here. That's bounding the total degree. And then these three right here, that's bounding each individual degree. That's basically chopping off, that bounds the X degree, that bounds the Y degree, that bounds the Z degree. So it's those. But then we're also bounding the sum. So this is the bounding the sum of X plus Y, and this is bounding the X plus Z and so on. And that's what these are. So we're basically that, and that. So you actually get this sort of it's a simplex that's truncated in some interesting ways.
It's a normal standard of permutation in Polynomial.
No, that's how that.
In fact, all of these are members of that family.
That's right, and we will see. And it turns out that Bezout recognized that this third species actually had 8 forms, because the question is, you have the total degree, but you have B1 plus B2, and then you have A3, and so how do all these guys interact? And so basically it's whether these guys can be positive or negative, sort of, there's 2 choices there, 2 choices there, 2 choices there, and so that gives 8 forms. And so here's some modern pictures that were created by Erwan Penchevra, and I'll talk about him a little later. And so here's the third species first form, and that's basically a version of this guy right here. Because you can sort of see in the middle there's basically a 6-sided figure. And then it turns out I actually want to go this way, because when you compare these two, what you discover is the main difference occurs right here. So right there I have an edge going this way, here it flips the other way, and that's a bistellar flip. And so going from here to here, I've done a bistellar flip. So this means I'm in the secondary fan of, I basically take all my normal vectors and I figure out, how can I, and when I look at all those inner normals, I get a secondary fan where the chambers correspond to the various possible polytopes. So here we're in one chamber, and this bistellar flip takes us to an adjacent chamber. And when you compare these two, what you discover is that now it's this guy that does a flip. So going from here to here is another bistellar flip. And then going from here to here, you can see that the bistellar flip occurs along this edge, going from there to there. So we're actually, so basically going from this way, we're taking a path through the secondary fan. So just, when I saw this picture, I was blown away. That, here's, Bezout, talking about a secondary fan in 1779. And of course, like I say, he didn't think at all geometrically. He really, his way of thinking about it really was in terms of, these inequalities. And so you'll see a lot of stuff like this in his book. And, but, it's really just wonderful stuff that's clearly going on here. And so let's think about this, like the third species, the first form. So that's, again, one of these guys. And so here's what it looks like. Here you have these inequalities, plus you have these inequalities as well. And so it turns out, though, basically, if your three polynomials have ones that look like this, and then so here I'm going to give the simplest version. I'm going to assume they all have the same Newton polytope. Although it turns out that Bezout would actually allow his formulas look more complicated because each three could have a different Newton polytope, but of the third species first form. Here, just to simplify life, I'm assuming they're all the exact same Newton polytope. And here's the formula that he gave. And again, that's just what the classic Bezout's theorem have, because again, I'm assuming they all three have the same Newton polytope. And then again, you get some, you subtract stuff, you add stuff, and so you get this interesting term. And of course, if you were to, prove this these days, this is basically an example of the BKK theorem. And so we actually have some very nice stuff going on here. And what I want to do is actually say a little bit about how did he try to prove this? Because this looks pretty sophisticated. And his proofs, of course, weren't completely rigorous by our standards. And partly he just didn't have the language to say things. And so to use his proof, I'm going to put it in modern forms. And I should say that the guy Penchevra that made the pictures, he actually has a paper on Bezout that actually gives the details of all this. So if you want to see the mathematical details of why this is correct in modern language, you can actually read Penchevra's article. And it turns out Penchevra's having trouble finding a place to publish his article, because when he tries the math history journals, they say it's too mathematical. When he tries the math journal, they say it's too historical. And this is something that definitely, it's certainly on the archive, but it deserves a good publication. And so anyway, so what he talks about, so again, so the FIR are given polynomials, the AIs, those are Bezout's special polynomials, and basically special in this case means that you're really using, so remember that the FIs all have the same Newton polytope P, and so here what you want is the monomials to be lattice points of 2P, and then of course when you multiply that by F, the sum lies in here. And he's actually interested in the dimension of the co-kernel of this, although the way he says it is useful coefficients and useless coefficients. And the useless ones are the ones coming from the image, because those you're modding out. And so he's trying to come up with a language for trying to express this. And it turns out that the number of lattice points, it's a multi-parameter Ehrhart polynomial, because it depends on all the parameters to define the polytope. And he has to worry about cancellations, and that's one thing that comes in a lot. And so he says things like, the number of terms cannot be made lower by introducing fictitious terms. And so somehow he's saying that things are sort of independent modulo stuff. And of course what that means is there's a Kazul complex working in the background. And when you read Penchevra's paper, he actually writes down the Kazul complex, proves the appropriate exactness, and then is able to actually use that to actually get Bezout's result. So Bezout is looking at some pretty hard stuff. You understand a little now about why his book is 500 pages long. And because, of course, when he gives the Bezout theorem, he didn't give just one Bezout theorem. Like for these 8 species for the 8 forms of the third species, he gave 8 theorems. He gave one theorem for each one. And so here's an example of sort of what his original book looks like. And for the modern reader, it's pretty hard. So this is for the second species, and so he has these sort of alternating some kind of things, and And it turns out that this is basically the number of lattice points. And it turns out all the polytopes all have the same Ehrhart polynomial. So that makes things work out pretty easily. And basically, all the polynomials that appear in this expression have the same nature and of the proposed equations, and of course notice here he's working with these inequalities or come from his conditions on being in the second species and stuff. So it's not easy reading for the modern reader. And but then the question is, how does he actually compute this number of lattice points? And the way he does that is basically he uses the calculus of finite differences. And so basically here's this number of lattice points, and that's a difference operator in the language of finite differences. And when you do the difference, this is some kind of multinomial coefficient. So in fact, what he has to do for about the first 100 pages of the book is work out this version of the calculus of finite differences for these expanded binomial coefficients. And then he uses these methods later, assuming that the exactness of the Koszul complex that's sort of implicit in his work, he's able to then derive his formula. So it's very impressive stuff. And probably not easy reading for the contemporary reader. And in fact, one contemporary reader was Poisson. And so this is when Poisson was a student at the École Polytechnique, and he probably wrote the article in 1779. He was 18 years old. He was a student. This was sort of his first math paper. And it was published in 1802. And so it's a memoir on elimination in algebraic equations. So here's the French. It says, and so notice that his language, he sort of uses a mix of the language of Kramer and Bezout, because Kramer talked about the final equation, Bezout talked about the resultant equation, so he's sort of trying to cover his bases and not offend anybody, and uses both. But he says that the degree of basically of elimination of all the unknowns except one. So again, that's that idea, you want to eliminate all the variables except one. And you have a number of equations equal to the number of unknowns. So again, working in that situation, still working affinely. It basically is, it cannot be bigger than the product of the exponents of those equations. So again, there's that multivariable Bezout equation. And he says it is, but then he adds something that I don't know if this is the first time this has been said, but here he's also pointing out something interesting. It is equal to the product when the given equations are the most general in their degree. So that's saying generically, it's the exact number. And so that, of course, is something that these days we're very aware of. That when you do the BKK theorem and things like that, that's sort of for a generic system, and you have to worry about what happens in more special systems. Then he also talks a little bit later about reading Bezout and his comment. And here, this is from a English translation. He says this important theorem is Bezout's. But the way he proves it is neither direct nor simple, nor is it devoid of any difficulty. And in fact, what Poisson does is he completely ignores Bezout's book, and he gives his own proof. He said, well, I can't figure out what this guy did, so I'll just do it myself. And of course, none of us have ever done that. And the way he does it is he does it by induction on the number of equations, and he uses the formula. And so you take the first n minus 1 equal to 0. That'll have finitely many solutions, and then you plug those finitely many solutions to the last one. And of course, that's now the Poisson formula. But where does he start his induction? Well, he clearly starts his induction with n equals 2. Where he cites Kramer in 1750, and this formula actually appears in Kramer. So if you read any treatment of the elementary introduction to resultants, the Sylvester resultant, one of the formulas they give, they proudly call Poisson's formula, but Poisson copied it from Kramer in 1750. And what Poisson really did was the n-dimensional version of it, and that's really Poisson's formula. And so that's where things stood at the beginning of the 19th century, because they had this clearly huge work done by Bezout, but like I say, it was really hard to understand. And so it took a while for people to sort of come up with their own approaches to stuff. And in fact, now going into the 19th century more deeply, one of Sylvester's first papers, so he was 26 when he wrote this paper in 1840, and he basically wrote down the Sylvester, what we think of as the Sylvester matrix, whose determinant is the resultant in the in the one variable case, and he described it as a solid square, m plus n terms deep and m plus m terms broad. And so I'm not an expert on the history of matrices, but for example, I don't know how common the word matrix was at this time. And so it's possible that's why he talked about solid square. He also said later that he basically came up with this on his own. So he had not read Bezout or Kramer or anybody else like that. And so this was sort of an independent discovery. And then, of course, things exploded in the 19th century. And so, and this is a very, very tiny list. And you'll see in a couple of slides just how tiny it is. Because, resultants, so Cayley wrote about it, Brill, Kronecker, Mertens, who was a student of Kronecker, Netto. And so some of these were, sort of some of the first really complete presentations of the theory of the dense resultant. Because it turns out that Kronecker had actually worked out a lot of the stuff, but his paper in 1882, he didn't really include a lot of the details. He just sort of laid out the intellectual framework. But he did a lot of the details in his lectures. And, but it turned out we've lost his lecture notes. They were sort of destroyed after World War II in a fire in a cave. And it turned out, so it survived World War II. It was the aftermath of World War II that did in Kronecker's Nachlass. And so we don't really know exactly what Kronecker did, but Mertens was a student of Kronecker. And so when Mertens started doing some publishing the theory of resultants in 1886, that was sort of primarily guided by Mertens. And that's really hard to read. And Netto came up with something a little more straightforward. And then, of course, one of the classic references in English is Macaulay's work that really laid a pretty good, solid foundation for it. And of course, Macaulay's work is still referenced to this day. And of course, the basic idea is that we now work mostly homogeneously. So we have n equations, but now we have n plus 1 variables because it's homogeneous. And this resultant is a polynomial in the coefficient, so that the resultant vanishes when the equations have a solution in projective space. And so a lot of the 19th century was devoted to sort of working out this sort of what we call the theory of the dense resultant. And they had a pretty good version of that. Now there's something else called a resultant system, and that I'm going to talk about in the next lecture when I talk about the fundamental theorem of elimination theory. And so I want to now I said that there was a lot of work done, and so to give you a sense of just how much. So it turns out that in 1907, Netto and Levasseur wrote an article in the Encyclopedia of Pure and Applied Math, and they had an article on elimination theory that was 97 pages long. And just here's what happened in the 19th century. And it turns out that in one sense they actually sort of gave up, because the article says the large number and variety of these memoirs relative to elimination makes it difficult to make a rational classification. So they said, we're just not going to try to classify. So they just said, here's roughly the list of what happened. And so in one sense, it's a good historical record, but it doesn't really have much reflection on what's going on. And yet it's clear that there was a lot of people, intensely concerned with aspects of elimination theory. And so the best reference I know is Penchevra, because we saw some of his pictures earlier. And so his PhD thesis, History of the Theory of Elimination, 317 pages. Now, it turns out that some of that deals with 18th century, some of that deals with 20th century. The bulk of it, though, is 19th century. So there's a lot that happened. So it's clear that I am omitting massive, massive amounts of stuff. And so to finish up, what I want to do is basically just give 3 examples of elimination from the 19th century. And so first I want to do Minding that gave a slightly more interesting version of sparse elimination. Because we've seen that Bezout had lots of sparse elimination, but it was very structured polytopes that he was working with, basically guys that looked like this. And Minding had a version that allowed more flexible kinds of things to happen. And so here we get some more more interesting take on sparse elimination. And then, Binet is, I think, one of the first people that introduced the idea about how resultants interact with intersection multiplicities. And so we'll talk about that. And so both of these were sort of, in a sense, developing the theory of resultants. And so that's one thing that happened in the 19th century. Riemann, on the other hand, I'm going to give just a little tiny bit from the paper of his about the genus of an algebraic curve, where Riemann was simply a user of resultants. He just needed to do some elimination theory. And we'll talk about sort of what he needed to do. So to start with Minding, so this is the paper on the determination of the degree of a through elimination found equation. This is typical German that sort of piles things on. And what's interesting is that parts of the 19th century, because notice that there's no umlaut there, it's UE. And yet he's German. So why is a German writing UE? Well, in Germany there was a phase they went through of sort of trying to sort of Latinize German. And so for example, that's why Max Noether and Emmy Noether spelled the name with the OE rather than the umlaut. So it was that intellectual phrase. And of course, in developments in the 20th century, that was pretty decisively reversed. They went back to umlauts in a big way. And and so here's his notation for trying to do stuff. And so he basically, so he's writing basically f as a polynomial in y with coefficients in x. And this notation means the coefficient here, that's just some polynomial of degree 2 in x, another polynomial degree 2. Here, this constant term will be a polynomial degree 5. And so that's sort of his notation. And when and so in general, that's what it means. And of course, when you then look at the exponents that can occur, you discover I have 2 Newton polytopes. And the way that Minding tries to, so the idea is that he basically wants to eliminate y. So that's his goal, eliminate y, just get a polynomial in x. And in his way of doing it, he's basically going to be using Bezout's, or rather Poisson's approach, and that he basically takes this first equation and solves it. So he takes that one and lets the solutions, be y1 through y5, because it's a 5th degree equation in y, and so it'll have 5 roots, and where these, where you have these 5 roots, and then when you sort of, do this, and again, that's just, straight out of Poisson, and then here you have to do some, stuff to clear denominators, and then you get the elimination thing. But he's not thinking of, he's actually thinking of these as Poisson series. So he's really using, fractional exponents. So basically, in fact, here's an example that if the polynomial was, x minus y squared, you'd actually factor it this way. And so here's the y1 and the y2. They're actually algebraic functions of y, and he's expressing those algebraic functions as Poisson series. And so he was working in that framework of stuff. But if you think about it, that's that's actually the context in which Newton introduced Newton polytopes. And so the slopes of the Newton polytopes, play an important role. And what he did was he basically, by just thinking about the slopes that you get here, and he was able to actually, from those slopes, he actually gave a formula that said from the slopes of the Newton polytope, the degree should be the following. And so you apply that recipe in this particular case, you get 58. And so that's how he does the elimination. And it turns out that this is actually the mixed volume of these Newton polygons. And so this is a genuine mixed volume computation that genuinely, these two polygons have nothing to do with each other. So this is definitely beyond the kind of stuff that Bezout did, because when Bezout would, do his kind of thing, he assumed that all, basically, he assumed his polygons always, were of the same form, and basically in the same chamber of the secondary fan. And this is something quite different. And this is something that Maurice Rojas and I worked out in 2003, because we actually did a translation of Minding's paper into English, and then just did a commentary about, showing how Minding's result really does turn into a mixed volume computation. And so it's clear that, besides the big emphasis on the dense resultant, there are other things sort of percolating in the 19th century that were certainly worthy of thinking about. Now here in Bonnet, so this is the Bonnet of the Gauss-Bonnet theorem, and but here his work on intersection multiplicity. So again, this is the memoir on the solution of two equations and two unknowns. And so he writes the equations. He uses sort of a F for the first one and a boldface F for the second one. And so then the idea is that you take, now in this case, he's not going to use the Poisson one. He's basically going to take each one of these and factor it. And again, the idea is that then each of the yi's is an algebraic function of y. So that's, again, this is an example of that. So when you do that factorization, you get a y1 and a y2, which again are now, he's thinking of those as just algebraic functions, not necessarily thinking of the Poisson series. And then he defines the degree of multiplicity of a particular solution. And basically what you do is you look at this product, and so basically you look at all, so these are algebraic functions, and so when I plug in beta, the idea is, they're trying to give me the x value, and so when I plug in beta, so I just pick the ones that actually give the same x value as this one. So this is a local object that, how many solutions basically correspond to this particular solution right here, and so he calls that the multiplicity. But then, of course, the full resultant is a polynomial in y. And again, assuming that your coordinates are generic, then basically Bonnet's multiplicity is the multiplicity of beta as a root of this polynomial, because, so here's the, Poisson version of it. But then when you figure out what f of that is, and so you plug yi into this one, you get this global object. But again, the ones organized this way give the multiplicity, and so out of this you actually get the fact that that the product of degrees is the sum of the multiplicities. And it turns out that in the book Ideals Varieties Algorithms, we actually give a proof of Bezout's theorem, and we don't define, and we basically use this approach. We don't talk about this so much, but we sort of use this resultant-based approach to actually prove this particular version of a Bezout's theorem over the complex numbers. And so this is where, again, multiplicities enter into the picture in a pretty nice way. And so the final thing I want to talk about is from Riemann in 1857. And he's talking about the genus of the curve. And so here, so this is the theory of abelian functions. And so he basically has a plane curve, but again, he has a bound on each degree. So it's the variables are s and z, and the degree of s is bounded by n, the degree of z is bounded by m. And he's assuming that there's r ordinary double points. And clearly he assumes that some of those double points can be at infinity. And he claims the genus of the curve, he used p for genus, is given by this formula right here. Now, I'm actually not going to give Riemann's proof of the genus formula. I'm going to give one step in the proof. And so the one step in the proof says that, well, we have to eliminate s from these two equations. So I'm eliminating S between F and F prime, and this is a discriminant. And so the question is, what's the degree of that discriminant? And so that's an important thing for Riemann. And of course, what's really going on is that when I do f prime of s, that means you're differentiating with respect to s. So in fact, his f prime of s, that's really this polynomial. It's the partial derivative with respect to s. And so of course, that lowers this degree by 1. And so I basically want to do, so I have this equation, and I want to, basically eliminate s, and what's the degree in z. And it turns out that, for example, we could actually, there's several ways we can do it. One way is when you look at the version of the Bezout theorem that Waring quoted, this applies perfectly because I've got a bound on each degree. And so I can just do it that way. So you get this one right here. Now these days, of course, we just use Bezout's theorem in P1 cross P1 because we have that, and when you do Bezout's theorem in P1 cross P1 for by degree nm and by degree n minus 1m, you get that almost immediately. But of course, Riemann, he ignored Bezout, he ignored this, he just gave his own proof. And so he's sort of reinventing the wheel. And of course, none of us have ever done that either. But on the other hand, none of us are as smart as Riemann, so what can you say? And so basically, I'm actually ending early, which is delightful. And probably means I spoke too fast, so I hope I can slow down. So I first wanted to convince you that elimination theory in the 18th century was more interesting than you thought. There was a lot more going on than just Bezout's theorem. And then also, if you think about it, in the 19th century, there was this huge emphasis on the, dense resultant, but there was a lot of other stuff going on where people were thinking about things in really interesting ways. And so for the next lecture, I'm going to move over to the 20th century where things get really fun. And I'll begin with the theory of resultants, but we'll see some quite different things along the way. So that's the end for the first lecture. So any questions?
So earlier you were talking about how Bezout basically got to elimination.
Right.
How does that compare with like broker basis methods?
So basically he would try to, he set up a system of equations and basically solve that system of equations. So he had one that would work, so what you'd have to do is just get this big linear system of equations and solve it. And so that was his way of doing, and that was the standard way of doing it. So I don't think it had any relation to, there's some stuff, there's some things in some parts of Bezout that come close to a Grosvenor basis method. We were taking remainders. So there's some stuff in Bezout I didn't talk about. But some of this basic stuff, I think, was just really solving linear equations. That was their basic tool.
I figured there was, because like you said, you got to make this little complex.
Yeah.
I think that this whole method of elimination where they look at it as the x's as coefficients is essentially a lexicographic Grosvenor basis calculation, which are just eliminating from the top degree of 1 downward by treating them as a very large system of linear coefficients. But lexicographic.
Right. Carlos.
How did you run into that thesis on history of elimination?
What?
How did you run into that?
It turns out that Joanna Liu sent me the link when it was published.
The whole thesis is available in the archive or just the page?
Yeah, the whole thesis, yeah. So it turns out there's the thesis that's in the archive, and there's also his more recent paper on Bezout that's in the archive. And the more recent paper on Bezout is in English, the thesis is in French. Yeah.
Earlier you mentioned that Bezout had this strategy for picking these polynomials to AIs, so that basically the AI systems and FIs would give, the sum of those guys would give you some polynomial one variable.
Right.
But did he provide the method for picking those AIs?
So what his method was, you pick the AIs, you start with undetermined coefficients, And then when you have that equation and equate coefficients, you get a large system of equations. And then he said, solve that system of equations. Great.
Maybe you said this, but how many species did he come up with?
So and so the answer is I don't know. And I should mention that Gauss, who did Discussiones in basically 1800, also used some of the same terminology. So when he talked about quadratic forms, he wanted to classify quadratic forms, and he had species, he had genera, and that's actually the reason we use the word genus now in mathematics comes from Gauss's use of classifying quadratic forms into various genera, which he got from Linnaeus.
I'll say, you also use the word sparse quite frequently.
Yeah.
So I just want to make sure I'm clear on what that means. So I think of that as like you're in somehow a boundary situation where you've managed to make one of these coefficients zero sort of by accident, which is a very special case.
Yeah. So I think in the 18th century they didn't think of sparse that way. They just thought that just certain monomials don't appear. And so this idea that, like in this case, that this is the degree in x, and the point is that I've put a bound on the degree in x. I've put a bound on the degree of y. So here this is the bound on the total degree, but I have some extra bounds. And so that was how Bezout thought about, when I use the word sparse, I'm just in the sense of, just not being the full Newton polytope. But, Bezout had very specific ways of trying to say, that he's going to, ways of restricting the Newton polytope. And then Minding is the one that came up with something that was slightly more general for trying to restrict things.
Any more questions? All right, let's thank David.